Hey there, YouTube. My name is Ash, and I'm here to help you crush your coding interview. I've been a professional software engineer for 16 years. I've interviewed with most of the big tech companies, and I worked at Amazon for a while on the Alexa team as a software engineer. So I definitely know a thing or two about coding interviews, most of which I've learned painfully through trial and error. So my goal is to help you avoid as much of that pain as possible and help you ace your next coding interview so you can land that software engineering job you've been dreaming about. So today we're going to be talking about one of the most common problems you're going to run into in coding interviews, namely, how do you traverse a binary tree in order? Now, I have a binary tree drawn here, and in fact, it's a binary search tree. The meaning of a binary search tree versus a typical binary tree is whether or not this property holds true. Namely, all the left descendants of any node have to be less than or equal to all of the parent descendants of those left nodes. So in this case, the 1, 2, and the 3 are to the left of the 4, and all of them are less than or equal to the 4. If this were a 5, that property would not be true. If this were a 5, that property would not be true. But because of the fact that everything to the left of any given node is less than or equal to the node it descended from, and then over here, all of the right descendants are greater than the node that they descended from, we know this is a binary search tree. Now, the whole reason I went into that whole explanation is because the in-order traversal problem derives its name from the binary search tree definition. Namely, if it's a binary search tree and we do an in-order traversal, the nodes will be in order. Namely, we will go 1, 2, 3, 4, 5, and 6. Now, the reason that this problem often scares people is because, number one, you're only given a reference to this root node, and you have to figure out where to start walking the tree. Number two, the solution involves recursion. And recursion is just one of those things that just kind of stretches your mind when you first see it. In fact, it's one of the most common things that throws programmers for a loop. So if you're having a hard time with a recursive solution to something, don't beat yourself up. It is just as hard for everyone else, and anybody that claims it's easy is straight up lying to you. In general, whenever you face a binary tree problem, you don't actually have to code up the tree node class that represents the individual nodes. I've written up a solution here for what that node class could look like, and you can see it's really quite simple. You can usually get away with just telling your interviewer, hey, I'm going to assume I have this class called node that has instance properties for the node's value and its left child and its right child. Now, do double check with your interviewer as to whether or not this is a binary search tree or a binary tree or some other kind of tree like a radix tree or a ternary tree or something else. Never ever make assumptions about the type of the data structure unless you're absolutely certain, and it never hurts to ask about those assumptions. You will never be docked points for trying to better understand the problem you're being asked to solve. All right, so let's jump into the solution. Now over here, I've drawn 3 different binary search trees. As I've mentioned before, I really like to draw out the problem as much as I can in just a couple of minutes. And honestly, you could jump up to the whiteboard and draw something like this within 1 or 2 minutes probably. And it's also a great way to walk the interviewer through the examples just to let them know, hey, you know what, I'm thinking through this, okay? I know what a binary search tree is, and I know they don't all look the same, and I know all 3 of these are valid inputs to the algorithm that you're asking me to build. And so let's go ahead and say const in order equals function, and this function is going to receive a reference to the root node of whichever binary search tree we're trying to walk in order. So let's just go ahead and call that node. All right, so let's go ahead and define a variable that is going to hold the result that we are going to return. So I'm going to say let result equal an array. And then at the very bottom of our function, we will return this. And that way, it'll be very simple to kind of follow along with what happened. So then we'll say if node which basically is saying, if this is not an undefined or null value, then let's go ahead and first, let's walk to the left. Now, when we walk to the left, as part of this recursion, we're going to assume that that walk to the left is going to return an array as well. If that doesn't make sense right now, just hold on for a second, and I promise I'll get to it. So the reason I even mention that is because we're going to use some array concatenation here, which may seem weird, but if you hold on for just a second, I promise to circle back and make sure I explain all of it. So we'll go ahead and say result equals result dot concat in order node dot left. And then we will say result dot push node dot value. Then we'll handle the right side by saying result equals result dot concat in order node dot right. And then finally, outside of our if loop, we'll go ahead and just say return result. In fact, I have a little bit of extra space on my whiteboard. How spiffy. All right, so let's go ahead and walk through this code. And in fact, the easiest way to even think about this is you have to think about it in the sense of delegating control, right? When we start looking at a function that recursively calls itself within itself, what we're really thinking about is imagine that you and your friends were trying to, I don't know, rake some leaves. And you said, hey, you know what? Why don't you go rake that side of the yard? I'll rake this side of the yard in the center, and you, other friend, go rake the right side. So between the three of you, you split up that job. But now let's imagine that really there weren't three of you. Let's say that there were 3 teams of you. So now after you've split that yard work into 3, each of those teams now has 1/3 of the lawn, and then they can further split that work amongst themselves. And so if there were 3 of those folks in each team, they could say, okay, well, we've got 1/3 of the yard between us. Now let's split that 1/3 into another set of 1/3, and we'll each do 1/9. And in the end, we've all gone off and done our pieces, and we've come back and we've reported that we've done this work and it's good. Hopefully that's a decent analogy. All right, so I just wrote a bunch of code, and it's not that many lines of code, but it's not the most easily understandable code either. What we're basically doing here is we're saying result equals result.concat. What this is doing is it's saying whatever array is in result, take that array, concatenate it with the array that's returned by inOrder node.left, and then return a new array that is the concatenation of those two. So that's why we have to do result.equals, because this returns a brand new array, and so now result is being replaced by the concatenation of whatever is in result and whatever it just took care of on the left side of the tree. Then it says, okay, we'll take the value of the current node I'm looking at and push that onto that result array. Push is just JavaScript terminology for append. So we put the left side, then the current node, and then we go concatenate the right side of it. So if this is seeming like it's at all, oh, almost forgot my semicolon. So if this is seeming like it is confusing, let's go ahead and walk through some examples and see how this code works out. So let's take a look at this in-order code and see how it works against these 3 binary search trees we've defined. So if I started up here and I was given a reference to the for node, right? So I come in here and I say, okay, let result equal an empty array. If node, well, it's the root node, so I know it is defined. So we jump in here and we say result equals result.concat in order node.left. So at that point, the control of the entire program shifts. So now we call this function over again, but this time we pass in the left node of 4, which is the 2. So then we come in here and we say, okay, now we have another result array. This is completely separate. If you want to do a little bit more research, you can go Google about stack frames and how your computer actually manages recursion, and you can find some really great diagrams out there. But anyway, so let's say we've got this 2. Well, all right, well, once we get here, well, the 2 has a left child. So now we call this function again, and now when we finally pass in node.left of 2, which is 1, things start to get really interesting. And the reason for that is because the recursion finally meets its end condition. Namely, 1 has no left or right child. So when this and this line each get called, they're both going to return empty arrays. But result.push is going to return a value of 1. So when this return result happens, it's going to be an array that simply has the value of 1. Now, this is where the recursion starts to combine and merge the results together. So remember, we called this from the middle of processing the 2 node over here, right? So we're processing this 2 node, and we called this on node.left of 2, which was the 1. And so now we're getting that result back. And so now result equals an array with just the value 1 in it. And then we push the 2 onto that. And then we say result equals result.concat of the right side. So then we end up getting the 3. And if you want to keep track of this, it's often easy to just go ahead and say, oh, okay, well, let me take a look at what this overall array is that we're building up. So far we visited the 1, then we visited the 2, we visited the 3, and now we're going to return this whole array of 1, 2, 3 to the 4 node. Remember, when we hit that 4 node, we said result.concat in order node.left, and we passed in the node 2. And so now we're able to say, oh, we just got this array 1, 2, 3. Let's push the 4 on there. All right, so now we've pushed the 4. And now we say, oh, okay, well, what's to the right of that 4 node? Well, it's this 6. So we then say, oh, result equals result.concat in order node.right, and it passes in this 6. And so we come to the top. We say, we have an empty result array. We say if node. Well, it's the 6th node, so we know it's defined. Then we call result.concat in order, and we pass the left of the 6, which is the 5. The 5 comes in. It gets an empty array here because it has no left child. It gets an empty array down here when we hit that line because it has no right child. But this right here will return a value of 5 and push it onto the array. So we push the value of 5. It returns that. And now the 6 says, okay, cool, you gave me a value of 5 that I just went ahead and concatenated onto my result. I'm going to push the 6 on there, process myself, and hey, I have no right child, so I'll go ahead and return. And now the 4 gets the 6, the 5 and the 6 that it gets to merge on there. To make it a little bit more clear, what we could say is we could say it looks a little bit something like this. We could actually say, well, it was like we had this 4, and we got this 5 and this 6, and then they were merged and concatenated together. Because that's really what's happening under the hood, is we get these fragments of arrays, but because of the way we've written our recursive function, they kind of get glued back together in order. And that's really the beauty of this in-order traversal. So you can go ahead and go through that here as well. Right? Here we see, oh, well, because of the fact that there are only left children, we're going to basically come here and say, oh, well, we have this 3. Let's go ahead and process the 2. The 2 says, oh, well, I have a left child of a 1. So then that comes back. That returns an array with 1 to there. That merges the 1 and the 2, and then passes it back up here, which then merges 1, 2, 3. And the same thing happens down here. The only difference is here, the parent processes itself, and then goes down the right children, so you'll end up with 1, 2, 3 again. So hopefully that was mostly clear. But just in case it wasn't, I've included a link down below to a GitHub repository that has the code for all of this stuff in JavaScript along with some unit tests. So that way you can go ahead and run the tests, you can modify the code, you can write some additional tests, and you can validate that you really understand what it's doing, and then you can go ahead and practice on paper as well. Practicing on paper is the absolute best way to really hone those skills and to really drive home that knowledge and to be able to perform well when you go to an interview. For some reason, if you practice on a keyboard, even with a plain text editor, it just doesn't go as well in terms of the results that you get. That's my personal experience, and it's the experience I've heard from several other people. Now, your mileage may vary, but this is just kind of what I've seen. All right, so hopefully you all enjoyed that video. I definitely enjoyed putting this together. I'm getting really passionate about trying to help people do better in their job interviews. And so please, please, please leave a comment below. Make any requests you have for future topics. This topic was actually the result of a request from a friend of mine who's studying for software engineering interviews right now. He told me that he just was not running across that many binary search tree problems in JavaScript, and he asked if I wouldn't mind doing a few. So you're going to see a couple more of these coming up too as I talk about different aspects of trees. But if there's anything else you'd like to see, please go ahead and let me know down below in the comments. Also, if there's anything at all that I said that seemed at all confusing or unclear, please, please leave a question below, and I will definitely try to get back to you as quickly as I can. Thank you, and have a really, really great week.